Good morning, students. Welcome to video lecturing class on dynamics of machines. So we'll continue with the problems on force vibration. So here is the next problem. Show that providing damping in vibration isolation is not useful when the frequency ratio is more than 1.414 or root 2. So here in this statement he has given one condition to prove us. Okay, so what he has given, the providing damping in vibration isolation is not useful when the frequency ratio is more than root 2. So now for that we can make use of that transmissibility ratio equation. So TR is given by 1 plus 2 zeta R square whole square divided by root of 1 minus R square whole square plus 2 zeta R whole square, where this R is omega by omega n and the transmission, and we have to assume that TR as 1, that is transmission ratio as 1 and zeta as 1. So then that equation number 1 becomes root of 1 minus R square divided by root of 1 minus R square whole square plus 2R whole square. So here also this is, for this numerator term, it is root is there. Okay. So in place of zeta and TR, you have to substitute 1 as the value. So now if you simplify this equation to get the value of R, okay, that is cross multiplication here, then squaring on both the sides. So 2R square and 2R square will get cancelled. So here you will get this equation as 1 minus R square whole square equal to 1. So it is like A minus B whole square. So A square plus B square minus 2AB equal to 1. So from this you can write it as R raised to 4 minus 2R square equal to 0. If I take R square as the common, I'm left with R square into R square minus 2 equal to 0. So therefore R equal to 0. Okay. So or omega by omega n whole square minus 2 equal to R square minus 2 equal to 0. But R cannot be 0 because it is a ratio of omega by omega n. So we can write R square minus 2 as 0. If you write that R square minus 2 as 0, R will be root 2. That means it shows that the vibration isolation is possible in the range of, that is omega by omega n equal to R equal to root 2, or it should be greater than root 2. Otherwise vibration isolation is not possible. Okay. So the next one is statement is a machine of total mass 68 kg mounted on a springs of stiffness 11,000 Newton per centimeter with an assumed zeta value damping factor as 0.2 full stop. The piston within the machine has a mass of 2 kg reciprocating motion with a stroke of 7.5 centimeter and a speed of 3000 rpm. Assuming the motion of a piston is to be simple harmonic motion, determine amplitude of machine, phase angle with respect to exciting force, transmissibility and force transmitted to the ground. Fourth one is phase angle of transmitted force with respect to exciting force. Okay. So first we'll try to list out the given data. He has given mass capital M as 68 kg, stiffness as 11,000 Newton per centimeter, which will be 11 into 10 raised to 5 Newton meter. Zeta he has given as 0.2 and M he has given as 2 kg, that is reciprocating mass, and he has given stroke length as 7.5 centimeter. So if you convert that one in, or if you calculate E from that, take half of that one. So it will be 3.75 into 10 raised to minus 2 meter. He has given speed as 1000 rpm. Okay. So now not 1000, it is 3000 rpm. So omega equal to 2 pi n by 60. So in place of n, substitute in place of m, you have to substitute n, you have to substitute it as 3000. Then you will get the value of omega as 314.6 radian per second. So now we know how to calculate omega n. Omega n equal to root of k by m. So k is 11.11 into 10 raised to 5 Newton per meter and m is 68. So from which you will get omega n as 127.19 radian per second. So from that you can calculate the frequency ratio, that is R as omega by omega n. You substitute those two values, you will get R as 2.47. The first question he has asked us to determine the amplitude of machine. So that is x max is given by m by m. Again this term because it is a reciprocating machine. Okay. So into E into R square divided by root of 1 minus R square whole square plus 2 zeta R whole square. So in this equation we know all these values. Substitute all the values. Okay. And you will get the x max as 1.2965 into 10 raised to minus 3 meter. Remember, while calculating this omega n, this k should be in terms of Newton per meter, and here this E should be in terms of meter. Okay. Then the second bit he has asked us to calculate phase angle with respect to exciting force, which is given by pi equal to tan inverse of 2 zeta r divided by 1 minus r square. That is tan inverse of 2 into 0.2 into 2.47 divided by 1 minus 2.47 square. That is root of. So which is equal to 169.04 degree is the phase angle. Then the third one is the transmissibility ratio you need to calculate. So it is given by root of 1 plus 2 zeta r whole square divided by 1 minus r square whole square plus 2 zeta r whole square. So here also you know all the values. Substituting you will get transmissibility ratio as 0.27. And also we know that the transmissibility ratio is given by ft by f naught. F naught we can calculate for the reciprocating system as m into omega square into E, which is equal to m value is 2 kg, omega is 314.16 radian per second, and E is 3.75 into 10 to minus 2 meter. Substituting you will get F naught as 7402.21 Newton. So substitute those values in this equation, you will get force transmitted as 1998.6 Newton. Then the fourth bit he has asked us to calculate the phase angle of transmitted force with respect to exciting force, that is pi minus alpha. So pi already I have calculated, minus alpha value, alpha equation is tan inverse of 2 zeta into omega by omega n, that is 2 zeta into r. Substitute those values. Pi is 169.04 degree. After substitution you will get the phase angle of transmitted force with respect to exciting force as 124.39 degree. Then the next problem is, the statement is a machine has a total mass of 100 kg and unbalanced reciprocating parts. Again it is a reciprocating only. Parts of mass 2 kg which moves through a vertical stroke of 80 mm with SHM, that is simple harmonic motion. The machine is mounted on 4 springs symmetrically arranged with respect to center of mass in such a way that the machine single degree of freedom and can undergo vertical displacement only. Neglecting damping, calculate combined stiffness of spring in order that force transmitted to foundation is 1 by 25 times of applied force when the speed of rotation of machine crankshaft is 1000 rpm. When the machine is actually supported on a spring it is found that the amplitude of successive vibration decreases by 25%. Find the first one is force transmitted to the foundation at 1000 rpm, force transmitted to the foundation at resonance. Third one is amplitude of force to vibration of machine at resonance. So first we'll list the given data. He has given total mass as 100 kg. Okay. Then he has given in part reciprocating mass as 2 kg, and he has given stroke length as 80. So with the help of that you have to calculate E value. So E equal to 80 by 2, 40 mm, which is equal to 40 into 10 raised to minus 3 meter. Number of springs he has given as 4, and the speed n is 1000 rpm. So the first one is we need to calculate equivalent stiffness of the spring. So equivalent stiffness of the spring, to calculate that equivalent stiffness of the spring, you should know the value of omega n. But here, to know the value of omega n, you should know the value of omega, or you can use any of the equation, that is either you can use the transmissibility ratio equation or amplitude equation. So in all the equation you are having omega n, okay, but with the help of given data, which formula is suitable, that thing you have to decide. So here what he has given in this statement, it is found that the amplitude of successive vibration decreases by 25% of 25%, that is not this here. The combined stiffness of the spring in order to transmit it to the foundation is 125 times of applied force. Okay, so the force transmitted is 125, 1 divided by 1 by 25 times of force applied. That is Ft equal to 1 divided by 25 times of F naught. And we know the transmissibility ratio equation as Ft by F naught. So in place of Ft, you substitute it as 1 divided by 25 times of F naught, so that you will get a transmissibility ratio as 0.04. And also he asked us to ignore the damping. So when you ignore the damping, transmissibility ratio equation is 1 divided by r square minus 1, where this r is omega by omega n. Omega you can calculate by 2 pi n by 60, so which will be 104.72 radian per second. So in place of r, you substitute as omega by omega n, and tr is known. So only unknown is going to be in this equation, omega n. If you simplify that, you will get omega n as 20.537 radian per second. Moving further, once you know the value of omega n, the omega n is given by root of k by m. So omega n square will be ke by m. Ke means because it is equivalent stiffness, you will get. So substitute omega n as 20.53, ke is unknown, and m is 100 kg. So if you substitute that, you will get equivalent stiffness of spring as 42,176.8 Newton per meter. Then the second thing is force transmitted to the foundation at 1000 rpm. Then the amplitude of successive vibration decreases by 25%, which he has given. So here you cannot avoid the damping because the amplitude is decreasing here according to the given statement. So x0 by x1 equal to x0 divided by 0.75 times of x0. That means the successive amplitudes are decreasing by 25% of the initial value. That means the next value will be 25% less, means its actual value will be 75% of the initial value. Okay, so that is what he has written here. So x0 divided by x1, in place of x1 it is 0.75 x0. So from this you will get that ratio as 1.33. Logarithmic decrement delta is ln of x1 x0 by x1. Substituting that, you will get the delta value as 0.288. And also we have the equation for delta as 2 pi zeta divided by root of 1 minus zeta square. So in this entire equation only unknown is going to be zeta. Solve for zeta, substitute the value of delta, so that you will get zeta as 0.0458. Now can calculate frequency ratio as omega by omega n as 5.1. Now the transmissibility ratio is given by root of 1 plus 2 zeta r whole square divided by 1 minus r square whole square plus 2 zeta r square or 2 zeta r whole square. So in this equation you know all the values, so that you will get the transmissibility ratio as 0.044. Also we know that transmissibility ratio is given by ft by f naught. So f naught is nothing but m into omega square into E. Substituting this and this tr value in this equation, you will get force transmitted force as 38.6 Newton. Then the next thing he has asked us to calculate force transmitted at resonance. So at resonance means omega will be equal to omega n. So that transmissibility ratio equation reduces to root of 1 plus 2 zeta whole square divided by 2 zeta. And omega equal to omega n, that some of the terms will vanish there. So substituting all these values, you will get transmissibility ratio as 11. So when the transmissibility ratio is 11, what will be the force transmitted to the ground? So that thing you have to calculate by using this formula. Again, f naught is same, m into omega n square into E. So here at a resonance you are calculating, so in place of omega you have to use omega n here. That is the difference you have to remember. Okay, because in previous bit here you used omega square, here it is omega n square, because we are calculating at resonance. Okay, so transmissibility ratio 11 is 11 from this equation. So substituting that, you will get force transmitted at resonance as 371.2 Newton. Then the third bit he has asked us to calculate the amplitude of vibration, force vibration at resonance. So x max at resonance is given by m into E divided by 2 zeta. So here also some of the terms will vanish because omega equal to omega n. Substituting those values, you will get x max as 8.734 into 10 raised to minus 3 meter. Then the next problem is a TV set of 25 kg mass must be isolated from a machine vibrating with an amplitude of 0.1 mm at 1000 rpm. The TV set is mounted on 5 isolators, each having stiffness of 3000 Newton per meter and a damping constant as 400 Newton second per meter. So determine, first one is amplitude of vibration of the body, that is TV set. Second one is dynamic load on each isolator due to vibration. So first we'll try to list out the given data. Stiffness of each isolator he has given as 3000 Newton per meter. Damping coefficient he has given it as 400 Newton second per meter. And the number of isolators are 5. Mass he has given it as 25 kg. Speed he has given it as 1000 rpm. And he has given the vibratory amplitude as, that is y, as 0.1 mm. So assuming that isolators are arranged in parallel, so we need to calculate the equivalent stiffness and equivalent damping coefficient, because the number of isolators are 5. In this statement he has not given that it is a equivalent stiffness or equivalent damping coefficient. So we need to consider that number of isolators also. So for that, equivalent stiffness KE will be 5 into 3000, 15,000 Newton per meter. Similarly, CE is 5 into 400, 2000 Newton second per meter. After that, the circular frequency of forced vibration can be calculated using omega equal to 2 pi n by 60. So n he has given. So from that you will get omega as 104.72 degree. And the circular frequency of undamped vibration omega n equal to root of Ke by m. So here we are using a Ke. In a hurry, don't use only the value of K. So that's why we have to check. We have to be very careful while reading the given statement, whether he has given the number of isolators or the number of springs. That care you have to take while calculating the equivalent stiffness. Okay, so if after substituting, you will get omega n as 77.46 radian per second. And then with the help of that one, we can calculate frequency ratio R equal to omega by omega n as 1.352. So equivalent damping coefficient need to calculate. We know the equivalent damping coefficient, the CE equal to 2m into omega n into zeta. That is, C is given by 2m into omega n into zeta. So in this equation, the only unknown is going to be zeta, because C is already calculated, m is given, omega n you have calculated, only zeta is unknown. So with the help of this equation, zeta you have to calculate it as 0.5164. So now the first bit he has asked here is the amplitude of vibration of TV set. Okay, so the amplitude of vibration of TV set, that is absolute motion, x by y equal to root of 1 plus 2 zeta into r into whole square, divided by 1 minus r square whole square plus 2 zeta r whole square. So in this entire equation, the only unknown is going to be this x, because y he has given the absolute, for the absolute motion you have to calculate the amplitude of vibration. So if you substitute all the values and if you solve for x, you have to get it as 1.058 mm. Okay. Similarly, the dynamic load on isolators, it is Fd is given by z into root of ke square plus ce into omega whole square. So z by, we know that z by y is given by r square divided by 1 minus r square whole square plus 2 zeta r whole square. So in this equation, we know all the values. Substituting these values, you will get the value of z as 1.126 mm or 0.1126 into 10 raised to minus 3 meter. So substituting this z value in this equation, you will get the dynamic load as 29 Newton. So this is the total dynamic load, but there are 5 isolators. So can calculate that dynamic load on each isolator as 29 by 5, that is 5.8 Newton. Okay. So these are some of the varieties of problems on the transmissivity ratio, or you can say the damped forced vibration, or the determination of amplitude of forced vibration or maximum amplitude at the resonance. Okay. So, and for the systems which are having the reciprocating unbalance or rotating unbalance, these are the varieties of the problems which we have solved. So we'll end the session here itself. So if you have any doubt, you can leave the comment in the comment box. Okay. So you try to go through all these problems so that it will be helpful for your examination. Thank you.